Hello everyone, in this video I will be discussing the basic structure of fatty acids as well as the different ways that you can classify a fatty acid. We will also use fatty acids and the different types of fatty acids to explain the differences between fats and oils. So before we talk about fatty acids, we need to first talk about lipids. A lipid is a type of biomolecules. Now the word lipids and fats generally used interchangeably in VCE chemistry, and it is a type of biomolecules that contains carbon, hydrogen, and oxygen. The interesting thing about lipid is that compared to the other two types of biomolecules, lipid is not a polymer. And in VC, we focus specifically on triglycerides. So there are other types of lipids, like phospholipid, for example, some of you may have heard of, but we are only going to look at triglycerides this year. And this is a basic structure of a triglyceride. So hopefully, first of all, you can see that the triglyceride contains three ester groups. So a triglyceride is actually a triester, so it has three ester bonds, which means that it is formed via a condensation reaction. And the reactants to make a triglyceride would be an alcohol, and the alcohol in this case is called glycerol. And the other reactants, or in this case you would have three of them, would be the carboxylic acid, and the specific acids in this case are fatty acid. Okay, so in general, a triglyceride is a triester that is made of one glycerol and three fatty acid molecules. We're going to look at fatty acids specifically in this video, and in the next video, we'll look at how we can actually form the triglyceride via condensation reactions. All right, so let's talk about what a fatty acid is. Now, as the name suggests, a fatty acid is an acid, so it consists of a carboxyl group, so specifically an organic acid, and the fatty part just refers to the incredibly long non-polar hydrocarbon chain that is attached to the carboxyl group. So I have an example of a fatty acid here that by no means you have to draw out, but you just want to appreciate the fact that the non-polar section is significantly larger than the carboxyl group in a fatty acid. So even though it has a polar section, because of the length of the non-polar section, overall the fatty acid will be insoluble in water. This is the reason why fats are insoluble in water. Well, one of the reasons. The other reason is because the ester group is not that polar as anyway. And also just worth noting that fatty acid chains exhibit what's called the hydrophobic effect, which means that all the non-polar hydrophobic tails tend to form a cluster away from water. So if you have something like you have the polar head, and then you have a very long non-polar tail, what's going to happen is that if you put a lot of these molecules in water, then they kind of look like this. Usually the tail looks a little bit shorter than this. So all the tails will form a cluster trying to stay away from water. And this is something that we're going to look at in more details later on as well. All right, so this is a list of some common fatty acids, and you can see that you can get fatty acids from a range of sources, both plant-based and animal-based. And you get a few in your data book, but I thought I'd just show you where they came from anyway. So there are a few ways to classify fatty acids. We're going to look at the first one now. So the first method of classification of a fatty acid is to look at it depending on the number of carbon-carbon double bonds present in the hydrocarbon chain. Now I have to emphasize here that you have to say carbon-carbon double bond in your answer. It's not sufficient to just say double bond because there is already a double bond in the carboxyl group. So if you just say there is one double bond, it's very confusing whether you're referring to the CO double bond in the carboxyl group or the CC double bond, which is part of the classification. So not enough to say double bond. So this is a point that has been raised in the past, especially in the exam. So you wanna, if you have to answer a question, you definitely want to specify CC double bond or just write this out and that should be enough. All right, so I think this is pretty self-explanatory. You can classify a fatty acid to be either saturated, so it doesn't have any carbon-carbon double bond present, or mono unsaturated, so one carbon-carbon double bond, or polyunsaturated, so it has more than one carbon-carbon double bond. So I think that's pretty self-explanatory. All right, so this is the table that you get in your data book. It's page 7, table 9, and the fatty acids are listed based on increasing number of carbon atoms in the chain, and they actually very nice these days. They give you the condensed formula, semi-structural formula, and you can tell very easily whether or not a fatty acid is saturated or unsaturated from this list. So obviously these three, so it will go as being saturated, and maybe M is mono unsaturated, and P is polyunsaturated. So if we go with that, I think it's fairly easy to classify. So obviously these 4 would be, and 5, these would be saturated fatty acids. So the mono unsaturated would be palmitoleic is an example, or oleic. And then the others, you just need to read the semi-structural formula very carefully. So obviously there's a 2 here. So linoleic acid has 2 CC double bond, so it must be polyunsaturated, as well as linolenic and arachidonic. I think you get it like 7. Another thing that I want to point out that may be of interest is, especially if you look at these 3, so steric, oleic, and linoleic, and even linolenic, so these 4, and they have the same number of carbon atoms. So if you look at their formula here, this is probably the best way to write a formula of fatty acid, because you can tell which part is the hydrocarbon chain and which part is the carboxyl group. But it can shows you the difference between a saturated version and a mono unsaturated version, and then the version both of these are polyunsaturated, but this one has 2 CC double bond, linoleic, and linolenic has another one, so 3 CC double bond. And you can see here that for the saturated version is C17H35COOH. So it's very similar to the general form of an alkane or a saturated hydrocarbon. So you can go like CnH2n plus 1 COOH. Now that would be the formula of a saturated fatty acid. And then for every carbon double bond that is added to the hydrocarbon chain, you're going to lose 2 hydrogen atoms. Once again, this is very similar to what happened when you go from an alkane to an alkene. So if I go to this, to mono unsaturated, I just go CnH2n minus 1 COOH, and then so you lose 2 hydrogen. And then if you want to add another CC double bond, you lose another 2 hydrogen. And then to add another, you lose another 2 hydrogen. So you could, with practice, or just by observation, you should be able to tell how many carbon-carbon double bond is present in a fatty acid just by looking at the ratio between carbon and hydrogen atoms without having to be provided the semi-structural formula. All right, so I think I have a general form here. So if you have the general formula being CnHXCOOH, then you can work out how many CC double bond that is present just by considering how this is the saturated version. So if you have n carbon, then the maximum number of hydrogen atoms that you can have is 2n plus 1. And then subtract the actual number of hydrogen atoms, so you can work out how many hydrogen atoms have been lost, and then you divide it by 2. That gives you the number of CC double bond. So in the case of the previous example, if I have C17H29COOH, let's say if I just give you this formula and you don't have it in the data book, you should still be able to work out how many carbon-carbon double bond is present. So 35 would be the maximum number of hydrogen that you can have, and then 35 minus 29 over 3, divided by 2 to give you 3. So that would be the number of carbon-carbon double bond present in the hydrocarbon chain of this fatty acid. Having said that, I haven't seen these kind of questions being asked recently, at all. Obviously I would do that. So I'm sorry, I'm gonna have to delete this. Anyway, so if I give you the formula, it's very easy to work out the number of CC double bond present. However, if you just have a fatty acid in a sample in real life, you probably wouldn't be able to work out the general formula. So how do we actually determine the level of unsaturation experimentally? And this is where addition reaction once again proves to be useful. The level of unsaturation of a fatty acid can be represented via what is called its iodine number. And this is the mass. This number reports the mass in grams of iodine. Now is a good time as ever to remind you that iodine is I2 and not just I. So this is a diatomic molecule. It's one of the few diatomic molecules that you need to know. So this is the mass of iodine that is required to completely react with 100 grams of the fatty acid. So basically you mix iodine with the fatty acid and you work out how many grams of iodine is required for a reaction. And that iodine number allows you to determine the number of carbon-carbon double bonds present. So let's talk about this a little bit more. We're going to talk about calculation of iodine number. Okay. Wow, and you know what? I have to say I'm quite surprised of how little details I have on that slide, but that's okay. So let's talk about iodine number. Let's say the question is to calculate the iodine number of arachidonic acid. So this is given here. And you know from the data book that there are 4 CC double bond present. Okay, so let's go back to the definition of iodine number. This is the mass in grams of iodine that is required to completely react with 100 grams of the fatty acid. So there are 2 things that I need to determine here. First of all, I need to know what kind of chemical reaction this is going to be. And second, I need to probably determine the number of mole of the acid so I can work out the number of mole of iodine. I'm going to do the easier one first, which is to find the number of mole. So I know mass of acid is 100 grams as per definition of iodine number. So in order to find the number of mole of the acid, I'm going to find the molar mass, and you have the, well, it's not molecular formula, but it's pretty close to, and it's, at least you don't have to count all the hydrogen. That would take a while. So you have 20 carbon in total plus 32 hydrogen and 2 oxygen, which is, so 304 is the molar mass that I have found. So you can find the number of mole of the acid, which is just mass on molar mass. Remember the day when this is the hardest thing you have to do. And you should get 0.3289 mole. So this is the number of mole of the acid. Now the important thing, however, is not to find the number of mole of the acid, but to work out what exactly is the chemical reaction taking place here. And I hope you can realize that this is going to be an addition reaction. So iodine is a halogen, and a halogen can undergo an addition reaction with a CC double bond without the need for UV light. So in general, if I just have a CC double bond, and if I react it with iodine, then the CC double bond will break, or one of the bonds in the CC double bond will break, and then you're going to have the 2 iodine atoms being taken into the carbon chain. All right, so let's just, and then you just have the rest of it. So the ratio here, it really depends on how many carbon double bond that is present. So the number of mole of iodine to the number of mole of acid, if you will, is going to be a 4:1 ratio in this case, because there are 4 carbon-carbon double bond present. So you can think of it this way: the number of mole of iodine has to equal to the number of mole of CC double bond present, because I'm sure you can recall the mole ratio in an addition reaction is 1:1. So you're gonna take up both atoms in that molecule. So for every CC double bond, you're going to need 1 iodine molecule. So if the number of mole of iodine equals the number of mole of CC double bond, then in this particular case, the ratio between iodine and the acid will be 4:1 because there are 4 C double bonds present in the acid. So number of mole of iodine is just going to be 4 times the value I found it earlier, and you get 1.316 mole or something like that. And I just need to find the mass of iodine, which is the definition of iodine number. So I need to find the molar mass. This is another potential part for mistakes because people just look at the molar mass of one atom and forgot to double. So you have to double. So the mass, a molar mass of iodine is 253.8 anyway. And final answer, the mass of iodine is 333.9. So I'm gonna go with, let's go with 4. So it's probably not 400. All right, let's go with 334 grams. So that's going to be the iodine number. There's a little bit of a roundabout way to report unsaturation, but it's a value that can be asked. So obviously, if a fatty acid is saturated, then the iodine number will be 0 because it doesn't require any iodine to react because it will not react with iodine. So if you have an iodine value of 0, you just know immediately that is a saturated fatty acid. All right, so that's the second classification, which is iodine number. So the mass in grams of iodine that is required to completely react with 100 grams of a fatty acid. And then the last level, actually no, this is not the last. This is still part of the first classification. Another sort of consequence of unsaturation is that, I mean, I'm sure you know this, but unsaturated fatty acids, similar to unsaturated hydrocarbons, would have lower melting points in general compared to the saturated versions of similar sizes. So I can't really compare if they have different sizes, but in general, with similar sizes, they will have lower melting points. By sizes, I mean number of carbon atoms present. Okay, so the unsaturated version would generally have a lower melting point and would appear softer at room temperature. And the reason for this, obviously, is because of the stacking. The unsaturated version will have carbon-carbon double bond, and the naturally occurring orientations of fats or fatty acid is the cis arrangement. So the cis arrangement would actually make it quite difficult for stacking to occur. And this produces a permanent band or a kink, which you may have heard of in biology. So there is a kink in the hydrocarbon chain, which prevents the fatty acid tails from lining up and packing closely together. So the dispersion forces formed between the chain would be much weaker than in the saturated version. The more unsaturated a fatty acid is, the more kinks that it may have, so the harder it is to stack. So obviously, if I go from saturated to monounsaturated in this case, and then polyunsaturated, so if I go from left to right, there will be a decrease in melting point. We don't really talk about boiling point for fats. It seems to be a bit silly because they probably will degrade before they even turn into gas, but it's really melting point that we're talking about. So there will be a reduction in melting point as the fatty acid becomes more unsaturated. And this also explains why saturated fats like butter or even the fat that you may see of like meat tend to be solid at room temperature. So butter is solid. I mean, it gets soft, but it's not like an actual liquid. Whereas oil, which is unsaturated, would be liquid at room temperature. And you can kind of control how easy it is to spread something. So if you want you want something, you don't want something to be completely liquid, but if you want it to be a little bit more spreadable, then you would control the ratios between saturated and unsaturated fats. And you see this in things such as do I have an example here? I don't. Yeah, but things like chocolate spreads or Nutella, which has a fair amount of vegetable oil. I mean, it's probably a lot of oil and nothing else. It doesn't even have chocolate in it. But you can change the ratio, and that allows you to improve the spreadability of the lipid product. Okay, that's enough about Nutella or chocolate spread. I don't know what I'm trying to do with this slide, so I'm just gonna delete it. And trans fat. So as I said earlier, the cis arrangement is the naturally occurring form of fatty acids, whereas trans fat is the unnatural version, if you will, in the sense that it normally only appears when you deep fried food. So somehow the act of deep frying turns the cis arrangement of, say, the oil, which is unsaturated, into the trans arrangement. The trans arrangement is a little bit easier to stack. So trans fat can have a slightly higher melting point than the cis counterpart. And this is still not a direct link, but there is a strong correlation between consumption of trans fat and increased risk in heart disease. I think there's some argument that it is a little bit harder to digest because it stacks a bit better, so it solidifies a bit more easily in the bloodstream, which is not a good idea. However, it's not a direct correlation, I have to say, but it's just the cis is the version you normally see in naturally occurring fat, and the trans is the version that tends to happen during cooking at high temperature. Okay, that's the first classification, which has to do with the level of unsaturation. The second type of classification only applies to unsaturated fatty acids, and you can classify fatty acids or unsaturated fatty acids according to the position of the C-C double bond with respect to the omega carbon. All right, so let's talk about a bit of Greek alphabet, if you will. So you have a carboxyl group in every fatty acid, and then there will be a carbon. Now, this is not only for fatty acid, this is general in biochemistry. The carbon that's linked to the functional group is called the alpha carbon in chemistry. And then the carbon that comes after that, it's called the beta carbon, and then you can go on. I don't really care about the alpha carbon at this point, but ultimately what will happen is you're gonna get to the very end of the chain. The very last carbon in the chain is called the omega carbon. So this is omega. Okay, so when we talk about position with respect to the omega carbon, you need to know which one's the omega carbon. So it's just the last carbon on the chain, if you will. If you count the carbon in the carboxyl group to be carbon 1, then the omega carbon is the last carbon. All right, so the definition is you have omega-3 fatty acid, which means that the carbon-carbon double bond is in the third carbon from the omega carbon. And then you can have omega-6 fatty acids, in which the CC double bond is on the sixth carbon from the omega carbon. All right, so I think I have an example here, and then I'll go back and look at the data book. So this is the omega carbon, as I just said. It's on the opposite end of the carboxyl group. And if the CC double bond, or the first CC double bond, is 3 carbons away, or on the third carbon from the omega carbon, then this is called omega-3 fatty acid, which is the main component of omega-3 fats, which some of you have heard of, I'm sure. And similarly, if the first carbon-carbon double bond is 6 carbon away, so 1, 2, 3, 4, 5, 6 carbon away from the omega carbon, then this is called omega-6 fatty acid. So you should be able to classify the unsaturated fatty acids in the data book to be either omega-3 or omega-6. Now, not every one of them is going to fit into those two categories. Some of them are neither, and that's fine. Like, obviously, none of the saturated is going to even bother with this classification. This one is neither. It's not 3 or 6 either. However, this is, so linolenic, so you can see 1, 2, and then the third carbon has a CC double bond. So this is omega-3. Pretty sure that was the example I just used then. And I can't count. Actually, sorry, this one is, so 1, and then there's 4, so that's 5 carbon. So the 6th carbon is where the first CC double bond occurs. So this is omega-6. And I do believe arachidonic is also an omega-6 fatty acid. You see a lot in fish. Okay, so that's a classification of omega-3 and omega-6. Yes, these are food that are rich in omega-3. Anyway, broccoli. I like broccoli. So that's the second kind of classifications. The third, I think this is the last one. That's the third and last way that you can classify fatty acids is depending on whether or not it can be produced by the human body. And the general rule of thumb, anything that's considered essential, it's because you cannot make it yourself. So essential fatty acids are basically the fatty acids that you cannot synthesize or the body cannot synthesize. So they need to be obtained from diet. These are the essential fatty acids. So linoleic, linolenic, and arachidonic. And notice how they are the omega-3 and omega-6 fatty acids that we classified earlier. And this is probably why you hear omega-3 and omega-6 in the commercials, because these are the essential fatty acids. So if you have to take fish oil supplements, for example, it's just so that you have the essential fatty acids in your diet, which are mainly these three, which are omega-3 and omega-6. And obviously non-essential fatty acids are the one that can be synthesized yourself. So you don't need to consume them from your diet. So eating fat is important. Okay. Anyways, that's the end of this video on fatty acids, and I see you in the next one when we combine the fatty acid with the glycerols to make some actual lipid. Thank you.